After we talked about the average rate of change and the average quotient, we are ready to talk about differentiation. Imagine differentiation as only as simple as finding the steepness of the slope. As you can see in the graph in here, you have a slope and you have this stickman crawling over the slope all the way to the top, then he decreased or decayed down the slope all the way down. So you can see the stickman started from 0, then he's going with a steepness of a grade of half or 0.5, and he's going with a more steeper curve. We can say steepness here is 3 as assumption. Then you go all the way here, you already passed the steepness, and now you start to decay the steepness. As you're decaying with the steepness, you can see the steepness is measured in minus. That means you are not elevating, but you are downgrading through the steep curve. So again, we have here this triangle. We have the base of 1 foot, and we have the vertical line of it as 0.5 foot. Now in English, we call it steepness. In this case, the steepness is 0.5 or half. While in algebra, we call it as a slope. So the curve that the stickman is moving on is called a slope. In this case, if you remember the slope, rise over run, that's a 0.5 over 1, which is 0.5, or half over 1, which is half. So the slope in algebra in this case is half, which is known in regular English as steepness. That equals half. In calculus, we call it the variation over y divided by the variation over x, being called as an equivalent to the steepness. In this case, we call it in calculus as derivative. Derivative is basically the rate of change. How does the rate is changing over y divided by how does the rate is changing over x. In this way, as the stickman is going over the slope, as you are moving with the x-axis, you are moving in values in the y-axis as well. So the slope here is the rate of change. We call it dy, which is derivative of y over derivative of x. We call it dy over dx equals half in this case, which is the slope that we know previously. Look at this curve for a function, or this linear representation of the function y equal 2x plus 3. Now, as you're moving through this function graph, you are moving through points in x and y, as we learned before. So you are moving all the way to the top. As you're moving one step, so here you're moving from 1 to 2. So as you're moving one step to the right, you are moving 2 steps to the top. As you're moving 1 degree on the x-axis, you are moving 2 degrees on the y-axis to reach the point 2 and 7. In this case, what is your slope? You're moving 1 degree on the rise, on the run, and 2 degrees on the rise. 2 over 1 in this case give you a slope of 2. Or you can use the slope that we learned before, y2 minus y1 over x2 minus x1. So you moved from point 1 and 5 to the point 2 and 7, which is here we defined x1 and x2. And we defined y1 as y2 as the initial and final point for that specific curve or steepness. And so on and so on and so on. If you want to go from this point all the way to this point, the run in here is 5 and the rise is 10. 10 over 5 give you a slope of 2. So it doesn't matter where you measure the slope for the same curve, as long as it's a linear representation for the function, then your slope will be the same, which makes sense. Now, we said for that specific slope, we have dy over dx equal 2. That means the slope of the rate of change of y over the rate of change of x equals 2. you read it as dy over, or dy dx, some people say dy over dx, equals 2. That's how you read it. So dy over dx equals 2. dy, how did we change in y? We change for 2 degrees, which is from 5 to 7. 7 minus 5, which is y2 minus y1, that's 2. And from x1 to x2, that's 2 minus 1, which gives you 1. The rise over the run, 2 over 1, give you 2. And that's the derivative of that slope at that exact point. Another representation for the derivative, you can have it as y prime equal 2. We call it y apostrophe here, can be called as y prime equals 2. Y prime exactly means dy dx, or dy over dx. Now, the derivative of the function y equal 2x plus 3, which is this function represented in this graph, equals 2. We will learn more easier ways to find the derivative, but that's the graphical way of finding the derivative of that function. You draw the function on the xy axis and you find the slope at any given point for that function, as long as it's a linear function. So the derivative, as we learned, is a rate. It is simply the measure of how much one thing changed compared to another one. If we get a real life simple example, we have here person A is double the weight of person B, and you have here a balance, and that's the center of the origin point of the balance. The person called A is sitting 1 time away from the origin, and person B is sitting 2 times away from the origin. So A weighs twice as B, and A is twice closer to the center of the balance as B. Now, how do we represent the derivative or the rate of change of motion for these two people who are playing on the balance? We can say the d of B equals to the d of A, which means the motion of B will be twice the motion of A. You can see here A is pulling down 10 inches and B is being pulled up 20 inches. In this case, we can say B is moving twice as much as A, so dB equals to dA. Or in other words, dB dA, or dB over dA, equals 2. And as simple as that, you found out the derivative. When you realize that B is moving as twice as A with time, then this way you found the derivative of that motion.